Hi, can you hear me?
Yes, sir.
Okay.
Judy.
Okay, so let's start. Yeah, we'll continue with the topic of inversion from last time. Before we start the actual discussion, just want to give you some visual interpretation of this inversion idea, because developing the intuitive sense is very important before we study the properties in more detail. So, I mean, till now, what we are doing is more or less just building up the framework, like the basic things, basic mechanism, like whether a line goes to a circle, under which conditions, and how to construct that locus, things like that. So, the one of the useful things about any geometric transformation, like inversion or even homothetic, anything like that, is it keeps some things constant, like invariant, and those are the things which are of interest for us. Okay, so it's important for us to study that aspect. So we will get to that today, and we will also discuss some interesting or quite powerful applications of inversion. I mean, so far we have only discussed what is inversion, but we are not really talked about why is inversion useful. Why should anybody care about this? So I think you'll get some idea of that today. Okay. So before that, let me just show you a couple of things. Okay, you can see my screen, right?
Yes, sir.
Okay, so you can draw this diagram in advance, but I think it got deleted. Anyway, it's not very hard to construct again. So if we start with any random circle as the circle of inversion, and we just want to study how various objects move with respect to this circle. So if I choose any arbitrary point P, okay, then how is this inverse look like? So by the way, I was going to construct the inverse through the like brute force mechanism, like AP into AP dash. But turns out there is a way to do that in GeoGebra. And I mean, I didn't know about this until I found it out. So in one of the transform tools, they have called it actually reflect about circle. So it's interesting. Even last time I was talking about this thing that really this is like reflection in a circle, just the way we reflect in a plane mirror. So I mean, the word reflect is very important here. So if I invert P with respect to this circle, like a P dash. So I mean, as I move the point P, you can see how the P dash also moves. And so if I enable tracing for both, okay. So now you can actually see that when I move this object in any complicated shape, so in a way you can say this is almost like the mirror image, that whatever object I can construct over here, it's almost like a mirror image in this, but it's not perfectly mirrored, it's distorted in a way, because I mean, what inversion does looks very funny in a way. The interior of the circle is a finite region whose area we all know pi r square, and exterior of the circle is an infinite region. So inversion is somehow mapping an infinite area region into a finite area region. So there is some distortion that is going to happen. It's not going to be a perfect reflection, but roughly you can get the sense that how when the P point comes very close to the circle, you see the inverse is also the close. At the circle, the two coincide, and the reverse also. As the point P goes inside, its inverse also goes outside. Okay. So I mean, just getting this intuitive sense is important. By the way, let me just color these two differently. Maybe so. We can color this orange, for example. Okay. So this intuitive sense is important. And by the way, I mean, there is nothing. I mean, orange is the inverse of blue, but blue is also the inverse of orange. Okay, there is inverse of inverse is back to the same object. So just get that intuitive sense of how inversion behaves. Okay. Then and another thing that we would like to see is that I mean, what I said last time, in the limiting case, I mean, if I take a circle of really large radius, okay, so let me do that. So I'll take B very far. Okay, let us work with this. I mean, I could take B even further, but for now, if I do this and now I zoom in this part, so I mean, the more you larger radius you take, this will be more like a straight line. So then you'll see that the distances are more preserved. So like any object I draw here, more or less it is almost exactly being inverted, just like if this was a real mirror. Okay, so in that way you get the intuitive sense that really inversion is like reflection. Once you have very large radius circle. Okay, and I mean I could take that center even farther to make this even more a straight line. So even here you can see there is slight distortion, but it is much lesser now. Okay, so that is an important thing to understand, that what inversion looks like. Then coming to the objects that we discussed earlier. So for example, if I have a line, okay, so if I have any line in the plane, so what is the inverse of this line going to be? Okay. So if I choose any point here, okay. So as we discussed, the inverse of this straight line. So if I take any point on this line, what is its inverse going to be? Okay. So this C dash is the inverse of C. And again, if I enable tracing for this, so as I move point C on this line, you see how C dash is moving. So it is describing a circle. Okay, and in particular at the point A, I will get an inverse which lies on this line itself. So if I invert A, I will get the diameter of the circle. So this OA dash is the diameter I'm interested in, and so this is the locus. Okay, so this again, let us color code everything as blue and orange. So okay, so the inverse of this blue is the orange, and again get a sense of how when the line blue comes closer, the orange circle increases in size. In the limiting case, when it is tangent, you see that the orange circle also passes through that same point of tangency. And then if I bring the blue line closer and closer, the orange circle becomes larger. And notice the point of this intersection, where any point on the circle of inversion will remain invariant. So that is why you see this concurrency happening over here. And if I keep moving this blue line closer and closer, you see now that orange line is almost a circle of infinite radius. And so eventually when the line blue passes through O, this blue and orange will coincide. Okay. And then on the other side, it will start becoming reverse. Okay. So, I mean, this intuitive sense is very important. Okay. By the okay, so this was basically a line, and now finally the case which we are studying now, we have not completely proven everything, but the case of a circle being inverted into another circle. So by the way, I mean, here you see if a circle is passing through the center of inversion, which is O, then it will become a line. But what about a general circle? So if I draw any general circle over here, we are interested to know what is its inverse. So like we did last time, I can consider the diameter, right? So if I consider these 2 points, G and H, okay, and I invert those. Oh, I think I mistake. I should consider diameter passing through the O. Okay, so the inverse of G, if it's G dash, and H is H dash, then the circle with diameter G dash H dash is the inverse we're interested in, right? And important to know, I mean, I think last time somebody made the conjecture, and typically, I mean, somebody we can make this assumption that the center will also go to the center. So I is the center here, but now if I construct the inverse of the E, you will see that the inverse of E is E dash, so it doesn't coincide with I. Okay, so in general, we cannot expect that the center will go to the center. Okay, but I mean, the two endpoints of the diameter G and H, they will go to G dash and H dash. So that part matches up properly. Okay. So, and I mean, then if I vary this first circle, okay, let's say I increase its radius, you'll see how if I increase the radius, the orange circle also increases. But important note to note, at all points of time, the O remains the center of homotheity for them. So, I mean, visually you can see that orange and blue, if I draw the common tangent, it will pass through O. And that makes sense, right? Because the point at the tangency will get mapped to the point of tangency on this orange circle also. Okay. And again, so if the circle is not intersecting, then you'll see the inverse is inside completely. In the intersecting case, you'll see again there is a overlap, the concurrency. Notice what happens if I keep increasing the radius. There is a point where the blue and orange circle coincide. Okay, and I mean this is something we'll study today, that if the circle is orthogonal to the circle of inversion, then it is self inverse. In other words, it is invariant. Okay, so a circle orthogonal to itself is not changed by inversion at all. But that is a bit misleading statement, because what is happening, if I take any point on this circle, okay, so if I take any random point on the first circle J and I look at its inverse, okay, so J is going to this point J dash, okay, but the circle as a whole is remaining invariant. So understand the difference between the circle. So in if I now the two circles are overlapping, but J is going to J dash. So the part of the circle inside our circle of inversion is getting mapped to the outside and vice versa. Okay. So it's not like every point is being invariant, but the circle as a whole is being invariant. Okay. And then one last thing I want to show you is, so we have constructed a lot of objects. So I want you to focus on all the, so that's why I actually color coded everything, because then basically the blue objects you can say are my input and the orange objects are my output. Okay. Now what happens if I change the radius of inversion? Okay, I'm only changing the radius of inversion, not the center. So look at what is happening to all the orange objects. So you see it's like a homotheity. So if I choose the radius differently, all I'm affecting in the inverted diagram is the scaling factor. But the relative positions of those objects are not changing at all. So this was the point I was making last time when we studied that one property, that the radius of inversion only affects the scaling factor. And in actual problem solving, this gives you the freedom to choose the radius anyhow you want. It doesn't really change the properties of the inverted diagram. Okay. So anyway, I mean, you could spend a lot more time trying out various ideas here, but just get an intuitive sense of how inversion works. And really, I mean, the analogy of the reflection is a very useful one in a lot of respects. Okay. So anyway, I mean, I think I was waiting for my tablet to start. Yeah. So then going back to our worksheet. Okay. So I mean, last time we were studying, we had to reach this point. Circle passing through the center of inversion inverts into line, and we are considering another general circle. So we just have to complete that too. Okay, so just to quickly recap where we were last time. Uh, so suppose we are given a circle of inversion, okay, and this is the other circle we are considering to be inverted, and we consider the diametrically opposite points A and B over here, and we got their inverses A dash B dash. And our claim is that the circle with diameter A dash B dash is the inverse of the first circle, right? So first thing we were able to prove last time is that O is the external center of homotheity. For the two circles gamma 1 and gamma 2. Right. And I mean, the way we did was simply by computing the ratio of the distances, like OB dash upon OA is equal to OB upon OA dash. We are able to show that this is equal to R2 by R1, if I call this radii R1 and R2. So then, having done this, we still have to prove that I mean, what is the locus about? If I have any random point over here on the first circle and a point Q over here, then we want to show that P and Q are inverses. So I think already last time we were on the right track for this. Having showed that this homotheity is there, I mean, it was only one step remaining. So let me choose the point P and Q on the inner side. Point P and point doesn't really matter. I mean, the proofs will be the same. Okay. So we need to prove that OP into OQ equal to R square, if R is my radius of inversion. And by the inversion we have constructed already, we know that OA into OA dash is equal to R square. So this part is already known. So then it's enough to show that the 4 points are concyclic, right?
So we had shown their concyclic
Yes.
last time.
We had done that they are concyclic. Okay. Can you just
Yes.
remind me what was the proof? So yeah, I think because O is the center of homotheity, if I consider the second point Q dash, I think that is what we had used, right? So basically, because of homotheity, what we can say is that B dash Q dash is parallel to AP, because B dash and A are corresponding and Q dash and P are corresponding under this homotheity.
Yes, sir.
And
Yes.
then now we can use the angles, because I mean, to show this concyclic property, it's enough to show any one pair of opposite angles is supplementary, and that follows directly, because now, for example, angle APQ is equal to angle, so AP, so B dash Q dash O, which is equal to angle
QA dash O.
QA dash O. Okay, so then basically these are the opposite exterior angles in this quadrilateral. So we are done. Okay, yeah, I think anyway, I mean, I indicated this last time, so we would have completed the argument on your own also. Okay, so yeah, so then I think that makes it clear that P and Q are inverses, and vice versa also. I mean, in locus problem, it's important to show the duality, that any point on the inner circle, its inverse will also lie on the previous circle. So that will also follow from this, because everything is reversible. Okay, so I mean, so hence the conclusion that inverse of a circle not passing through the center of inversion is another circle. And I mean, for our reference, it is a good thing to calculate the actual values also. So I mean, if I assign some numbers to that, so if the first circle, I mean, what are the values I need? So the radius of inversion I'll require, and let us assume that the first circle, if I call the center O1, then I need the distance O01 and its radius R1. Okay, so if I give you the values R, O01 and R1, I should be able to find the radius and the distance. So I should be able to find O02 and R2. in terms of these values. So I'll leave this for you as an exercise. Okay, we will not do it right now. It's just a calculation because you can take the two diametrically opposite points and use them as the reference to this calculation. Okay. So then now, as I said, that now we are done with the basic mechanics. We know which objects go into which other objects. But the question is, why is this inversion useful at all? So there comes the idea of invariants. So invariants are objects which do not change under this operation. So already we know some invariants, like for example, any point on the circle of inversion doesn't change because that point will be self-invariant, self-inverse. Okay, then any line passing through the center of inversion. Okay. So these are two invariants you already know. And just now I mentioned another one, which is a circle, which is orthogonal to the circle of inversion. Okay, so the first two we understand, but why is this two? Why is the circle orthogonal to the circle of inversion going to be invariant? So you can try to prove that. I'll give you a few minutes to try. Actually, one way is that if we find this formula, right? If we find this mapping, then we can use that directly to conclude this. In fact, for that reason, I'm thinking whether we should do this calculation right now or not. But anyway, I mean, we can derive this property even without doing the calculation. Okay. So if you have a circle which is orthogonal to your given circle of inversion, okay. So to construct an orthogonal circle, what do I need to do? If I take any point on my given circle, I draw a tangent over there, and on this tangent line, I have to choose the center anywhere. Okay. So if I choose the center O1 here, and then the circle with radius O1P. Okay. So this is my circle, which is orthogonal to the given one. So the question is, why is this circle invariant? Can anybody see why this circle will be self-invariant? Yes, Parth.
So because any point on the interior of the circle on that circle will go to every point on the exterior of the circle, because suppose it is A. So OA into OB is equal to R square.
Yeah, correct, exactly. So this,
And the,
yeah, correct. So this OA into OB equal to OP square, which is R square, which means that exactly A and B are inverses with respect to each other. And in particular, the points of tangency P and Q are self-invariant under this same operation. So in fact, I mean, another simpler way of saying the same thing is that, I mean, this orthogonal circle, its inverse will also pass through the points P and Q itself. So the inverse of this circle is another circle passing through P and Q. Okay, and then that is the same circle. Okay, so these are the three invariant objects. There is one more invariance under any inversion, which is also interesting, and that is the angle of intersection. Angle of intersection between any two objects. So this is also invariant. Now, do you remember what is the angle of intersection? I think we may have briefly described or given the definition, or very vague definition of this before. If you have any two objects, so when I say objects in our geometry, we will always talk about circles and lines, but this property is true for any two curves in the plane. So any two random curves like this in the plane, if they intersect at a point, I can talk about the angle of intersection of these two curves. So how can I define that? If you have any idea?
The angle
And
between
it's that point to the curve.
tangent to the
Tangents, correct? Yeah. So if I draw at this point, if I draw tangent to both the given curves, then the angle between these two tangents is what I can call the angle between these two curves. And I mean, here there is a ambiguity, like which angle are you talking about? Is it this one or this one? So, but any one of them is fine. So, I mean, that ambiguity, probably there are ways to resolve it if I assume some direction and things like that. But for us, it's enough to say that any one of them is we can call the angle of intersection. Okay. So, as it turns out, if I take any two objects and I invert them in some circle, then I'll get some new objects in that inverted diagram. Okay. Then the angle of intersection remains invariant. So that the tangent line itself will not remain a line because line will become a circle. But in the inverted diagram, again, if I draw tangents at that point, then turns out that these angles are preserved. Okay. Now, I mean, proving this for a general curve is quite tricky. In fact, we don't have the necessary tools to do that. I mean, how you define a curve and etc. We don't know. But we could do this for the objects of our interest. So, for example, when I'm talking about angle of intersection between two lines, it is just the typical angle we are talking about. So, if these two lines get inverted into two circles, okay, then what is the angle at those two circles, etc. So, like there are several cases we have to consider here. Like if the original objects are a line and line, I mean, in one case, if the two lines are passing through a center of inversion, they may become two lines itself. Or maybe one of them passes to the center and one doesn't, then it will be a line and a circle. Or it could be a circle and circle. So there are several cases to be considered. And similarly, if you have a line and a circle to begin with, they may become like line and line, etc. So there is a whole matrix to be considered here. Okay. And maybe with some simplification, we don't need to consider every possible pair because some of them will be just repetitions. But yeah, I mean, we could do this whole exercise and prove that in every case the angle of intersection remains invariant. Okay. So I don't want to do that right now. I mean, it mostly just exercise of doing some angle changing and things like that. But this whole set of properties is useful, which I've summarized in just one line, which is the angle of intersection between any two objects. And in particular, there are two angles which are of particular interest to us. One is tangency and the other is orthogonality. Okay. So tangency is obviously if I have a circle and a line which are tangent to each other and they get inverted into something else, then they may be inverted into circles and I mean a circle and another circle. Then also the tangency will remain. Or if it becomes a circle and a line, then again the tangency will remain. Okay. By the way, I mean, if you think about it, this can never become a line and line because if it becomes a line and line, it means that the two lines were passing through the center of inversion, which is not possible. And similarly for orthogonality also. So orthogonality in the case of lines, when I say orthogonal, I mean perpendicular, obviously. So if I have two perpendicular lines, then through inversion, they will become orthogonal circles. Okay. And vice versa. So these are the two cases to be considered in particular, okay? Tangency and orthogonality. So I mean, in a way, I feel this justifies when we are doing orthogonality earlier, many times I has to write like circle gamma 1 is perpendicular to gamma 2. So I mean, this is not an official notation, but now we really see that this perpendicularity and orthogonality are just two different ways of saying the same thing. So there is a lot of similarity between these two ideas. It's just we are talking about the angle of intersection between two curves. That is all it is we are talking about. Okay. So having studied all of these things, we should try and use inversion in some interesting way. So one of the typical classical applications of inversion is a theorem called Feuerbach theorem. Can you raise your hand if you have heard this term before? Three or four people have raised their hand. It's a very interesting theorem, and it really connects a lot of ideas that you have seen in a separate ways. So, for example, in a triangle, okay, we all know there is a in-circle, X-circle configuration. So, if I consider the angle bisector, okay, then I can consider the in circle over here. And I could consider the X circle opposite to vertex A. Okay, so this is the in circle X circle configuration. And we also know there is orthogonality, like the orthocenter, circumcenter, 9-point circle configuration. So for example, if I just consider any 2 points on the 9-point circle, so I'm taking the midpoint of BC and the perpendicular here, and I need one more point. So okay, so this is the 9-point circle. Okay, and what the Feuerbach theorem says, which I have tried to denote in my rough diagram, is that the 9-point circle is tangent to the in circle and the 3x circles. Okay, so the in circle and x circle come from a very different place, angle bisectors, tangent circles, etc. And 9-point circle, as you know, comes from the center or circumcenter, orthocenter, that side of things. So the Feuerbach theorem really connects these two seemingly separate configurations and unites them into a single configuration. So 9-point circle is tangent to the in circle and x circle. And there are several proofs of this. There is one proof using pure trigonometry also, which I'll have to recall. I have not seen that in a long while. But the typical example of how to prove this is using inversion. Okay, so we will study that proof right now. And I mean, that is like one of the powerful applications of inversion. We will see really how to connect the information we have studied so far, all the properties, and how to really use them in a practical example. That is what we want to do right now. Okay, so by the way, does anybody already know this proof using inversion? Maybe you have seen it earlier somewhere.
Sir, we know using trigonometry.
You know the proof using trigonometry. Okay, I see. So I mean, this was part of the typical lectures which you have done.
Yes.
Yes.
I see. Okay. Okay. So then you know the trigonometry proof. Then in fact, maybe later on you have to help me to remember that proof. I have not done it in a while. But now let me tell you the intuition behind how we are going to use inversion. So what is the strategy we want to follow first? So and in this we are going to use all the parts that we have done before. So you know that in any, if I have any two circles, I can draw several tangents. So I can draw the direct tangent, the inverse tangent, things like that. So in this case, for example, the two blue circles, okay, the in circle and the x circle. If I consider all of their tangents, what can you see that I've already drawn which are the two direct tangents? So direct common tangents are the
AB and AC.
AB and AC, correct? And I can draw the what do we call it? Indirect tangents, internal tangents. I forgot.
Transfer.
Sorry,
Transfer.
transverse tangent. Yeah, correct. Correct. So then, which are the so if you see here, BC is one transverse tangent, but there is another tangent which I can draw, which is not there in the diagram at all. Okay, and that will obviously it will pass through this point where the angle bisector meets the base BC, correct? So that other transverse common tangent will look something like this. Okay. So this is what I want to do. Let us consider a circle. So the midpoint of base BC is also drawn in this diagram. You see, so that is this point, to which our 9-point circle passes. Okay, and I deliberately drew these perpendiculars also. So by the way, do you know anything else about? So if I call this feet of the or the points of tangents is D and D1, and this midpoint is M. So we know that M is the midpoint of BC,
DD.
and it is a midpoint of DD1 also.
Yes, sir.
Yes, sir.
This is known because basically BD and CD1 are both equal to S minus A. Okay. So then if I consider a circle with center M and radius MD dash, or in other words, a circle with diameter ED dash. Okay. So if I draw this light blue circle over here. Okay. So this light blue circle is my circle of inversion. And through this circle, we are going to invert the whole diagram. And we want to see what all happens. Okay. So let us start to write down like under inversion through this object. And let me just make some space for this.
The
Okay.
in-center becomes the x-center. X circle. The in-circle becomes the x circle.
Okay. So which are the objects of my interest? So let us start with the simplest one. So what about line BC? So where does line BC go?
Sir, it remains B.
It will remain line BC only because it is passing through the center of inversion, which is M. Okay, so line BC remains unchanged. Okay. What about the incircle? So incircle is the circle with center I and radius ID.
Sir, it will also remain as it is because it is orthogonal.
Exactly. So the point to be noted is that the circle, incircle and excircle, they are both orthogonal to this blue circle. Do you see that? Because at the points D and D1, there is a 90-degree angle being happening. So the incircle and excircle are both orthogonal to this blue circle. So therefore, the incircle will remain invariant. And the excircle, so we are only talking about the excircle opposite point A. So we are doing everything with respect to only this pair I and I1. Excircle will also remain itself. Okay. So this is our claim. This purple line which I've drawn, right? If I just call it line L. So this line L, which we know is a common tangent between the incircle and excircle, we are going to show that this line and the 9-point circle are inverses. If we show this, then what does it imply? Because we already know that this line L is tangent to the two circles, incircle and excircle. And the important property that we discussed is that angle of intersection remains invariant. So tangent objects remain tangent objects. So do you see that will complete the proof?
Yes, sir.
Because if line L is already tangent to incircle and excircle, and then through inversion, line L becomes a 9-point circle, and the other two incircle and excircle remain themselves. So then that means that the 9-point circle is also tangent to the excircle and incircle. That is the strategy. So to do that, what we want to show is this line L and 9-point circle are inverses under this light blue circle. Okay, so this is the strategy we want to use. And I mean, along the way, we did several smaller conjectures which are straightforward, which are basically the incircle and excircle being invariant. Okay. So then this is the last remaining piece to be shown. Okay, so with that information, I'll give you a few minutes to try this. Maybe I'll draw the diagram again because now because we have simplified a lot of things, we can only keep the objects of our interest and remove everything else. But this is the conclusion which we want to show that. So if I draw I'll only draw the part relevant. So we have.
Sir, but what about the other two X circles?
So if I do this, then I've shown that the 9-point circle is tangent to the incircle and the circle opposite A, correct? Now, if I can repeat the same argument with, so here I took M, which is the midpoint of BC. You can imagine if I took the same circle on the other two sides and repeat the argument, there also the same thing will happen, right?
Yes, sir. Yeah.
Okay. So by symmetry, I mean it's the Feuerbach theorem is about 4 circles in total. It's the inner circle and circles I1, I2, I3. But if we show I and I1, then by symmetry, then I2 and I3 will also follow symmetry.
Yes, sir.
Okay. Okay, so then if the problem is clear to you, you can start trying it again. Meanwhile, I'm just drawing the diagram a little more cleanly so that we are only looking at the objects of our interest. And we can choose some common notation. So, I mean, the midpoint of BC is point M. It's slightly dislocated. Then the angle bisector. So here I'm choosing the case where AB is smaller than AC. So that, I mean, that affects the order of objects on the line, but as such, the overall argument doesn't change. Okay. And somewhere on this line, there will be the in center I. So D is the point of tangency of the in circle. And similarly on this side, I'll have point D1. So I will not draw the X circle for now. And so this is our circle of inversion. And under this circle, we want to show that the 9-point circle this circle becomes the so another important thing to be added is that purple line. So going back to the original diagram, here we described that purple line as the other common tangent. Is there another way of describing the same line which is easier to draw or construct? So if I zoom in particular, the line BC is already one tangent. So what can you say about the angles being formed here? Because remember this line I1, this is a line of symmetry. So do you see that it's we can say this angle and this angle are equal? Okay, are you following me? So if I take one of the tangents BC and I reflect it in the line joining the centers I and I1, I will get the other tangent. So I can do the same thing over here. So I don't need to construct that purple line as a tangent. All I can say is that I reflect the line BC in the angle bisector and I will get the other line. Okay, so I've just constructed this line so that these two angles are equal. So then this line L is the other common tangent, transverse common tangent between I and I1. Does that make sense?
Yes.
Okay. So now then given all of this, now we have to prove that L and NPC are inverses. Under gamma, if I call this circle gamma. Okay, so I won't give you any other hints for now. I'll just let you think and figure it out. Okay, so I will give you the answer, but just to break this problem into smaller ones. So this is always the trick. How do you break this seemingly complicated statement into something simpler that we can prove? So to prove that this line and circle are inverses, what is sufficient? What are the things that if we show those things, then we are done? So firstly, the circle is passing through the center of inversion already, right? The red circle is passing through M. So we already know that the inverse of that red circle will be a line. So there is no question about that. So then we just need to characterize that line uniquely, what that line is going to be. So for example, to define that line uniquely, you can fix, let's say, one point on that line and the slope of that line. Okay. So for example, if we consider in this diagram itself, so the foot of the altitude from A. Okay. So let us give this point some name, P, let's say. Okay. So if what our claim is true, what should be the inverse of P under this light blue circle? If the red circle is going to become the purple line, then where should the point P go? I mean, we have to prove this, but where do you expect it will go?
Sir, where the angle bisector meets PC.
Correct? So the angle, so this point, if I give it some name T, okay. So this is one of the things we can prove that P and T are inverses under gamma. So this is one thing we can prove. So if we prove this, then what it means is that the inverse of the 9-point circle is some line passing through T, but we still don't know which line. Why should it be purple line L? It could be any other line. So then what is the other part that we need to do is the slope of that line. So we know that the inverse of a circle, I mean, if I consider the 9-point circle, the center of the 9-point circle over here. Okay. I'm just drawing it roughly. I hope it is accurate. Okay, let's assume that this N is the center of the 9-point circle. Okay, then from our theory, it doesn't look like the center at all, unfortunately. Okay, so I'm just drawing it vaguely in the air. So then what is the other thing that if we prove that, then that will define the angle of line L uniquely. Going back to all the intuitive diagram that we saw, do you see it's enough to show that Mn is perpendicular to the line L? Because I mean, how do you construct the inverse? If I take the diametrically opposite point of M, okay, if I call it M dash over here, then what is the, how do you construct the line L? You take the, sorry, I can call this M dash. Okay, it's okay. I mean, typically we use the dash notation to denote the inverse point. Here I am using it a bit differently, but anyway. So the inverse of this M dash point will be a point on this line L somewhere. And then through that we draw the perpendicular to the line MM dash. So thinking about that in the reverse direction, it's enough to show that if Mn is perpendicular to the line L, and there is also from the point 1, already one point on the purple line and the red circle which are inverses, then it forces that the inverse of the 9-point circle is this purple line.
Sir, I didn't get why M1 should be perpendicular to L.
Mn is perpendicular to L because, I mean, if I just draw the diagram separately, if I have any circle and so this is a circle of inversion, and if I draw any circle passing through this point, okay, then what is the inverse of this circle?
A line.
It's a line, right? And how do you construct that line? So if I take the diametrically opposite point of this circle, if O P is the diametrically opposite point, then what is the inverse of P? It will be some point P dash, right?
Yes, sir.
And then the inverse of this circle is this line, isn't it?
Yes, sir.
So the line joining the center of inversion and my original circle ON has to be perpendicular to L.
Understood.
Okay. Okay, so these are the two things we have to prove. And if we do that, then we are done. Okay, so if what you can try doing the second part first, okay? MN perpendicular to the line L is follows more directly from the typical angles we know in a orthocenter configuration. You can raise your hand in case you already done the second part. Okay, Jen. So you did the second part or the first part also?
Sir, the second part.
Okay. Okay, so I think if you're done with the second part, then the first part is, I think, more direct calculation based on distances that you already know. Okay, so let us look at second part, Mn perpendicular to line L. So the way we define line L, I mean, remember it is the direct or the other transverse common tangent between the incircle and excircle, but that description is very complicated to work with. So that's why we came up with the alternate way to define the same thing, which is we just took one common tangent, which was line BC, and we reflected in the line I1, which is line joining center. So that is why this is another way of constructing the same line L. Okay, so if that makes sense, then what are we interested in is the angle between Mn and line L. So we will do it in two ways. Like we'll first look at the angle of Mn with line BC and the angle of L with line BC. Okay, so we'll use like BC as the reference to find all the angles of our interest. Okay, if we do that, then the problem will be easier to track. So for example, first consider the angle that line L forms with the base BC. Okay, so in particular, if I just take any point, let me just take any point K over here, just to define the angle. Okay, so I'm interested in the angle KTC. Okay, so KTC is the angle formed by line L with the base BC. So how can I rewrite this angle KTC in terms of something which I already know? So do I know this purple angle which I marked in the diagram, angle ATB? How much is angle ATB equal to?
180 minus B minus A by 2.
180 minus B minus A by 2. Or I mean, I can directly use the exterior angle theorem because this is A by 2 and C, right? So I can directly write it as A by 2 plus C. And they're both equivalent. What you said is also correct. Okay. So then if this is angle ATB, then the twice of that purple angle, which is angle KTB. So this is equal to A plus 2C. Okay. So then if this is A plus 2C, then the angle KTC, which is the supplement, will be 180 minus A minus 2C. And I can do some simplification here. If I replace 180 by A plus B plus C, this will become simply B minus C. Okay, so angle KTC is equal to B minus C. Okay, so this was the first part. Now angle Mn with base BC. So what is the angle formed by Mn with base BC? So let's say I want to look at angle NMB. So here we have to use the known facts. So what is the diametrically opposite point of M on the 9-point circle?
X.
X, right? So it's the midpoint of the orthocenter, and so if I call H as the orthocenter, then X is the midpoint of AH. So basically, instead of talking about angle NMB, I can also talk about angle XNB. Okay, so angle formed by XN with the line BC. Okay, then going further, what else can I say about this angle? So if I just draw so now this is like typical orthocenter configuration. So in the orthocenter configuration, we know so we are interested in the angle formed by this line XM with the base BC. But do we also know that this XM is parallel to AO?
Yes, sir.
They form a parallelogram, right? So then in effect, I am interested in the angle formed by AO with the line BC. But how much is angle HAO?
B minus C by 2.
It is B minus C.
C by 2.
B minus C, right? HAO. Because
Sir, B minus.
B minus C, right? Because basically this both of these angles are, this is 90 minus B and this angle is also 90 minus B. So I'll get this is B minus C.
Yes.
So then I think are we done? We have all the parts required to finish this proof. Because if angle HAO is B minus C, then the angle formed by AO with the base BC, this angle will be 90 minus that. So this angle, if I call this point Q temporarily, then angle AQB is 90 minus B minus C. And that will also be equal to the angle XMB. Okay. So therefore, this angle XMB in our original diagram was angle NMB. So therefore, the angle formed by MN with base BC is 90 minus B minus C, and the angle formed by line L with BC is B minus C. So they are obviously complementary, and therefore this is true. Okay, so I mean there could be some other way of doing the angle chasing also, but in essence, what we are using is the known properties of our orthocenter configuration. Okay, so then what that achieves is that uniquely defines the slope of line L. So the slope of line L is correct, but still there are infinitely many lines of the same slope. So what does guarantee that the 9-point circle and the purple line are inverses? For that we need the first property, that if we show any one point are inverses on the two objects, then that line is completely uniquely defined. So for that we chose the pair P and T. Okay, so then for that it's enough to show that P and T are inverses of each other. And in other words, what is it enough to show?
MT into MP is equal to MD the whole.
Yeah, correct. So it's just a numerical calculation now. So if I show that MT into MP equal to MD square, then I'm done. And then, I mean, now this is all lengths or distances on line BC, which we know, because what are these points we're talking about? Point P is the foot of the altitude. Point D is where the incircle touches. T is the angle bisector intersection, and M is the midpoint. So we know all distances. If I like consider B is my reference point, like the origin, then I know all the distances like BP, BD, BT, and BM. All of these are known quantities which we have used at some point or the other. So I can put everything together and finish this problem. Okay. And I mean, again, if you can be a little bit more smart about doing the calculations, you can keep things simpler also. So, but in any way, I'll give you a few minutes to try and finish those calculations. And meanwhile, let me think if there is a non-calculation way to see the same thing also. That would be interesting. But I mean, that may be hard because in a way, to do that non-calculation way is equivalent to the Feuerbach theorem itself, which we know it's a very powerful result. So it would be interesting if there is a simpler way to show the same calculation. Okay, can you raise your hand if you're done this? Okay, so how do we do this efficiently? As I said, my initial idea was to use B as the point of reference. I'm trying to think if there is a better strategy, but at least for now, I don't see anything. So let's start writing. So BP is nothing but anytime you have to do calculation like this, we have to choose at the outset what are our fundamental variables, because I mean there are several ways to write the same thing. Finally, if we reduce everything to just a few handful of variables, then things will cancel out. So we have to choose what are those variables. So one option is we have to use the sides of the triangle ABC and use write everything in terms of those strictly. Okay? So like ABC are my fundamental variables, I can say. Or if somebody wants to go by trigonometric approach, then some of the values will be slightly different. So for now, let us use the sides ABC as the fundamental reference. So in that way, then what should be the value I should write for BP? So how do I obtain BP through that? So one strategy is in triangle ABP, BP is nothing but C into cos B, and cos B you will know through cosine rule is nothing but A square plus C square minus B square upon 2BC, and the C will cancel. So BP can be written in this way. Okay, and finally we are interested in the distances from point M. So from this I can write MP is nothing but A by 2 minus this. Okay, and we can simplify this further. We will do that soon, but I just want to write down the basic expressions first before we do any simplification. So this is BP. Then what about BD? BD is the distance of the tangency, that is S minus A, or in other way it is B plus C minus A by 2. So if BD is this, then MD equal to, and by the way, throughout this question, I'm assuming that AB is less than AC. So the order of the points is fixed because of this. If the AB was greater than AC, then everything will happen on the other side, but doesn't change much actually. So MD is nothing but A by 2 minus this. Okay, and then finally BT. So BT is the distance of the angle bisector, how much it makes on one side. So that will be equal to 8 times C by B plus C. Therefore, MT is equal to 8 by 2 minus this. Okay, so at least all the objects of interest are on the table now, and what we have to prove is MP into MT equal to MD square. That's what we have to prove. And now, in theory, you should be very confident that once you have done this, this has to follow. Like the calculations in some case may be easy or difficult, but there is no other way now, because this is because we have chosen the variables ABC, and everything is in terms of those, and we all know those are independent variables. I can choose ABC anyhow I want, obviously under the triangle inequality, but for in essence they are independent variables. So now there is no two ways about it, that if I expand everything from here, I should get this. Okay, so that confidence you should have now, and then with that you can do the calculations correctly. In some cases, like what happens in a problem you are doing in an exam, you have too many unknown variables and you have to show some result, and it's not guaranteed to you whether it will come out or not, because I mean, see how I smartly eliminated here. There was cos B. Just imagine what would have happened if I left the cos B as it is and I continue to simplify. Then your expression would have A, B, C as well as cos B. Okay, that's a not a good thing to happen, because now there is an interdependence in your variables themselves. So then, I mean, what can get cancelled, what cannot get cancelled is very tricky. So the first most important thing when doing any calculation is try to come to some independent variables, whatever it be. Like maybe you chose some different variables. For example, the whole thing can be done with another set of independent variables. Somebody could write A, C, and cos B as my fundamental variables, which is perfectly fine, because you can imagine that all of these three things uniquely define the triangle and you can choose them independently. So the choice of variables is up to you, but the important property is independence, that you can choose all of them separately. Then everything will work out is guaranteed. Okay, so let us continue to calculate this. So I mean, first thing we can clear the denominators and simplify these expressions. So let me do that. So MP can be written also as if I keep 2b in the denominator, so this is AB minus A square minus C square plus B square. MD is equal to minus minus. So this is basically 2A minus 2 minus C by 2, and MT will be equal to 2B plus AC minus 2AC. So it will be basically equal to 2B minus AC. Okay, so on one side we have to compute MP into MT, and on the other side it is MD square. So MD square, I'm just thinking how we can simplify this a little bit more. So I'm just thinking of writing it as this way. So then finding its square might be somewhat simpler. And MP into MT also, is there any way of simplifying the calculation? Okay, I don't see any obvious way.
Sir, I think BD should be S minus B.
BD should be S. Oh yes, you are correct.
Yes, sir.
BD should-
And
So
MD
we
should
get
be B
cancelled.
minus by 2.
Okay, so BD, yeah, I mistake. BD should be S minus B.
Sir,
Yeah.
also in where you have taken cos b denominator as b, so shouldn't it be AC?
Oh yes, you are correct. So then it should be 2A, right? Not 2B.
Sir, 2AC.
2AC, but then the C will cancel, right?
Yes, sir.
So it will be 2A. Okay, good. Maybe I should rewrite them. Several mistakes are there. Yeah, I was wondering because I mean I did this last time. I felt that the calculations are not that hard. So there was some mistake. So then we- so BP is this term, BP is K by 2 minus by 2. Yeah, I mean actually there was one red flag. Unfortunately, I erased everything. The red flag which I was seeing that something is wrong is the asymmetry. So what this question, if you see, everything should be symmetric with respect to B and C. So if that is not happening, then there is some mistake. Yeah, but good that we got this right now. So then from this we get MD is nothing but A by 2 minus A plus C minus B by 2. Okay, I think MT was correct. Okay, let me repeat the calculations again. So then MT is, so now I think there are more things cancelling out. So MP, if you see, A square will cancel out. So it will be simply B square minus C square upon 2A. Okay. Then MD is, again A by 2 will cancel. So this is simply B minus C by 2A. And MT is equal to AB minus AC upon B plus C. Yeah, now in fact this is looks a lot more straightforward because there are many things which will cancel out. Okay, I think now can you see the result directly? Here itself I see a lot of things are common. So when I take MD square, so there are like 2 copies of B minus C in the numerator and 2A into 2A. So this will be equal to the product of these two. If I multiply this and this, then I can see that term by term everything will cancel out because this B plus C will cancel out with the B plus in the denominator, and B minus C and B minus C will become B minus C whole square, and 2A and A, what is happening there?
Sir, MD should be only B minus C by 2, not 2A.
Oh, there is no 2 in the denominator. Yeah, sorry. So there will be a 4 in the denominator, and then so this A and A will cancel, but there's still one factor of 2 which is I'm not able to explain. Oh, yeah, I think here I will this should be 2 times 2 plus. So there is a factor of 2 here also. Okay, so then this will also cancel. Okay, so everything is cancelling now. Anyway, I mean, sorry for the mistakes in calculation, but I mean, overall approach, I think everybody has understood. So you can work out
Yes.
the details. Okay. And I was just thinking, I mean, while I gave you some time to try this, how can we do this without calculations at all? So, I mean, I just came up with a rough strategy. I don't know the details, but if you are interested, you can give it a try. So, what do you want to prove? MT into MP equal to MD square. If I show that, I mean, there is another circle I'll be drawing here. Consider the circle with diameter 80. Okay. So if I consider a circle with diameter 80, so it will have the midpoint of 80 as the center. Will be some completely different circle. If I show that this circle is perpendicular to gamma, my circle, that is also enough. Okay. Because then what that will imply is that what is that enough? Yeah, because that circle with diameter 80 passes through P also. So therefore TP MT into MP will be equal to MD square. Okay, so this is an alternate thing which you can try to prove. I mean, I have no idea how to do that, but I feel it will be simpler because then I don't need to consider point P also. So there is some simplification happening there, but anyway, it's just an idea at this point. Anyway, so this completes the proof of Feuerbach theorem, but let me just recap and explain the important steps because we did a lot of things from the start. So most important thing is the overall strategy. So to prove Feuerbach's theorem, which means to prove the in circle and the 9-point circle are tangent, we found a circle which can be used for inversion, under which a lot of things remain invariant. So that was this blue circle, the circle with diameter DD1. Okay, the fact that under inversion through this blue circle, the in circle as well as X circle remain unchanged. Okay, that was the one of the important things we realized first. And then based on that, now the other object we want to show is tangent, which is a 9-point circle. It gets conveniently inverted into the common tangent, which was line L. So that was the first thing that we understood, that this is what we want to prove. And then actually proving that the line L and 9-point circle are inverses, that itself we broke into 2 small parts. So the first part was to rather the second part which we did first was just the angle of intersection. So that was MN perpendicular to line L. And then the first part was to show any 2 points are inverses on these 2 objects, because then that will uniquely define the line L. Okay, so that was the overall strategy. So this explains, or at least give you some demonstration that how you can use the various parts of inversion or rather properties you have studied so far and put them together to solve a problem like this. Okay, so that was Feuerbach's theorem. I'll give you a couple of minutes to write down anything you want. Unfortunately, the proof is so big I cannot fit it on one slide, but I can just scroll if you are interested. Okay, so with that we have completed the theory of inversion, and now we can turn to do some actual problem solving. Let me just check if there are any other properties that we should know in advance. So the question H was the calculation one which I left as a homework, that if I actually have a circle, how can I find the radius of the inverse circle and things like that. So you can work it out. And like one of the consequences of this formula you will see is the orthogonality. So if the original circle is orthogonal to the circle of inversion, then you will see that R square equal to OP into OQ. So there is no inversion happening at all. But apart from that, I think we have done everything. There are some problems F and G which we did not cover, but I think they are just there to illustrate the properties of inversion, just to give you a little more intuitive sense of how inversion works, etc. Okay, so I think we can use those also as exercise. Okay, so we have some time. We can try solving a couple of problems. So start with problem A. Looks like I have only one question A, and after that everything is from shortlisted problems. But anyway, so maybe we won't have time to do more problems, but at least we can finish problem A today.
Sir,
Yes,
so one IMO problem was also left from cross ratio topic. We did not solve it.
from cross ratio term. Okay.
It's the last problem. I think we forgot.
Oh yes, yes, I remember now. Yeah, it's an interesting problem actually, but I don't know if we have time to do this right now. And I will also have to remember the proof. I don't recall it offhand. But anyway, yeah, while you try problem A, let me also take a try at that one. I think question A is quite simple, so we will finish it in no time. But I will require more time to do that other problem. Okay, anybody has solved this question? Okay. So you don't need to use anything difficult for this problem. Just the definition of inversion is enough. Okay, so what do we have? So what is being asked? We have the circumcircle of ABC and the incircle. So what is, we want to use this incircle as the rate circle of inversion. Okay, and we want to invert the circumcircle. Actually, I don't even need to draw the circumcircle for this question, but just to illustrate. Okay, so the question is, what is the inverse of this circumcircle with respect to the incircle? So it's enough to consider any 3 points of the circumcircle, and if I find their inverse, then obviously the circle passing through those 3 points is the desired locus. So what is the inverse of point A with respect to the incircle? So I am interested in the point on this line, okay, such that IA into IX is equal to R square. But so do you already know some properties about the diagram? Where will this point X lie? Or rather conversely, I can consider the midpoint of FE. Okay, so the point where FE meets AI, everything is symmetric with respect to the line AI. So obviously this is also the midpoint of FE. So then do we already know this? Ix into IA equal to IX square.
Yes, sir.
Okay, so then therefore A and X are inverses under the inversion in the circle, in circle. And the same thing will happen on all the three sides, right? So just as A and X are inverses, similarly here B and Y will be inverse, and here C and Z will be inverse. So if A is going to X, B is going to Y, and C is going to Z, that means the circle ABC will become circle XYZ. And XYZ is nothing but the 9-point circle of triangle DEF. Okay, are you able to follow this? Jadip, you have any other proof for this? So, I mean, in a question like this was just based on the definition of inversion. So, all you need to really do in this question is when I say the 9-point circle, out of those 9 points, which point you have to choose? That was the only thing which was not clarified. Okay, so here, I mean, choosing the midpoints of the sides of triangle DEF, those are directly like 1:1 correspondence with the vertices of triangle ABC. Yes, I think we don't have enough time to do another problem. Question B. Yeah, I think question B will require some time to think. So anyway, we'll continue this topic next time. And also that other question, I'm just looking at it. I'll require some time to work out the solution. So this will also discuss next time. Or I can post the solution on our group. Anyway, this is a IMO problem, so the solution will be documented already. So I think we'll end our class early. Let me just check if there is anything else to be discussed. Yeah, nothing for now. Actually, question G is an interesting property which you should know. It has a practical value for solving any problem. That if I start with two circles which are not concentric, can I construct an inversion which will make them concentric? Okay, that could be useful in some cases. But yeah, we'll see that at some point. Okay, then if I have some time, let me do the puzzle which I started talking about last time. Jadip, you have raised your hand. You want to add something?
No.
Okay. Yeah. So yeah, well, last time not really a puzzle, but interesting application of binary numbers. So the what I mentioned briefly was, for example, if you have a case like suppose you want to send a word like hello. Now there are several ways to interpret this. One is like you are saving it to the hard disk, and then later on you load the file, or simply it is a transmission of the information from over the internet. So from one computer to another computer, you want to transmit the information. Now the physical wire cannot transmit the letter H, but what it can transmit is a sequence of binary digits, that is 0 and 1s. So some combination of 0 and 1 I have to transmit, and the information should be recoverable on the other end. So important thing is it is a lossless transmission. So whatever information I send, from that the other person should recover the original information. Like if I sent hello, he should be able to look at the string of bits 0 and 1s and say that okay, hello was sent. So that this is the challenge for us. Let us take a very simple example of, let's say you have a language having only four alphabets, A, B, C, and D. Okay. So then how many bits will you require to encode a single character? So 2 bits are sufficient, right? Because I can write A as 00, B as 01, C as 10, and D as 11. Okay. And now, so for example, if the first computer is sending the string 00011111, let's say. Okay. So then looking at this, the other person knows what is the information being stored or being sent, because what they can do is they can break this incoming stream at these intervals of 2. And so now they know that this is A, B, C, C, for example, sorry, A, B, D, D. Okay, so this works very nicely. And on an average, so these are called symbols, by the way. So I'm introducing some technical definitions or technical notation rather. So these are called symbols. And the question is how many bits per symbol are required to transmit on average. So how many bits do we require currently? So in order to transmit four symbol word like ABDD, we require 8 bits, right? So on an average, it is 2 bits per symbol. And that is obvious because like every symbol requires 2 bits to be represented. So we require 2 bits per symbol. So the whole question is, can we do something better? Can we do this more efficiently? So for example, in the English language, we know the vowels are more frequent. Let's say even in this language, whatever this ABCD alphabet we have, A appears more frequently. So for example, normally any 4 characters have only 25% chance of appearing, but let's say A occurs 50% of the time. Okay. So like half the times you will transmit A. And then B has maybe 25% chance of appearing. So 1/4 of the times B will appear, and C and D both have 12.5% chance. So 1/8 and 1/8. So the total is 1. Okay. So having more this information that A occurs more frequently and BC less frequently, D even less frequently. So what we can do is we can assign a smaller symbol to A. Why should we assign the same length of 2 bits to everything? The symbol A, which is going to be transmitted more frequently, we can assign maybe 0 to this, and B can be assigned maybe 0, 1. C can be assigned 1, 0. We can come up with something like this, right? But
Yes.
can you see there is some problem with this? Suppose I do it this way. What is the problem?
Sir, when we transmit this,
Hmm.
the computer will not know how to make the partitions to interpret the letters.
Exactly. So if I just use this example I showed above, so this is same sequence 0, 0, 0, 1, 1, 1, 1, 1. So I can break this up into various ways. For example, I could break it like this. Now the meaning is A, B, D, and I could break it in some other way. Actually, in this case, there is only one way to break it. Or I mean, for example, let me take a deliberately confusing example. Okay. Suppose I am transmitting this. Okay. So now you will see there is ambiguity because I mean maybe the starting is still this is A, this is B. It is still unambiguous. What can I do to make it more ambiguous?
So will it work if you take the second last digit as 1?
In this example, so this is 1.
Yes. Second last digit, sir.
Second last. Okay, so 0, 0, 1, 1, 0,
0,
1,
1,
0.
0. Yes, sir.
Okay. So now what is ambiguity?
So in 001100 is also there is also ambiguity there also.
So you mean we drop the last digit entirely like this? Yeah. So here I can see the ambiguity is when this 1, 1 can be D and this can be AA. Yeah. What is ambiguity?
Sir, there can be a 1-0 for C.
Yes, so 01 and then 10 is A,
Yes.
01.
Okay.
Yes.
So for example, this could be AADAA, or this could also be this is A, this is A, B, C and A, for example. Okay, so the same set of bits, and I mean, I did not work out this example in advance, otherwise we could come with a more convincing example. But anyway, you get the point that it is not uniquely decodable. Okay, so the reason why the first method works is what we call fixed length encoding. Fixed length encoding, because the length of every symbol is fixed. It is 2 bits. So that is why making the partition is very easy. Whereas this is called variable length encoding. And because it is variable, this ambiguity comes about, that where I make the partition. But as it turns out, this is a problem with only this mapping. I could come with a different mapping which is unique. For example, I could come with a mapping where A is given 0, B is given 1, 0. Okay, so this is a mapping. If you can work out the detail, but this is actually unique in the sense that now any symbol or any bit length of bits I transmit, there is always a unique way of decoding and getting back the original message. Okay, so we want to solve two problems at once. So first is unique decodability. It should be unique to decode. Okay, and second is why we are doing this in the first place. We want to reduce the average bits required per symbol. Okay, so we need to come up with some mapping table which achieves both of these simultaneously. Okay, which can be uniquely decoded and the average length of the bits is reduced. So for example, you can take this example itself where I give A as 0, B as 1, 1, 0, etc. We can work out how much is the average length here. So A on an average will occur 50% of the times, and it requires 1 bit to transmit. Then B occurs 25% of the times, and it requires 2 bits. And C occurs 12.5, and D 12.5, and they in fact require more than 2 bits to transmit. So it may seem that we are making the situation worse, but note that C and D are less frequent. So even if they require more bits to transmit, on an average, what will happen? So on an average, this will only require half bit to transmit, because one will going to occur 50% of the time. Then 25% of the time will transmit 2 bits. So really it's 2 upon 4. Then this is 3 upon 8 and 3 upon 8. Okay. So if you add up all of this, what is the value that you get? So if I take everything in terms of denominator of 4, okay, so you see the total is 14 upon 8. So that is around 1.75. So now with this scheme, you see on an average, I require only 1.75 bits per symbol, whereas previously I required 2 bits per symbol. And still the information will be recovered. So the end user can decode and get back the original information. So that is what we have achieved. So we have achieved some level of compression of the information. Now this was the most simplest example which I could give you. But I mean, applying the same idea in a more complicated ways is what the zip file algorithm does. When it zips a document and unzips it, it goes through your data. It calculates the frequency of every letter. So it depends. Now here we used ABCD individual letters. Zip may look at individual words, like in the English language, the word "the" will occur more frequently. So "the" as a whole, it will be assigned some pattern of bits, etc. And like that, it will assign some pattern to every sequence of information, and in such a way that both of these are achieved, that unique to decode, and it reduces the average symbols count, average bits per symbol. Okay, so we still not answered the question how we constructed this table in the first place, and why does it satisfy both of these properties. So we will look at those aspects in the next lecture. We don't have time right now. Okay, but yeah, I mean, this is all part of a topic called information theory, and the reason I'm showing all of this to you is because basically binary numbers form the basis of a lot of these ideas, and we will be using binary numbers in a big way in the coming puzzles also, and in fact in some of the Olympiad topics also, for example, base representations in a general base K also requires some of these ideas. Okay, I think that's all for today. Thank you. Bye.
Thank you, sir.
Thank you, sir.
Thank you.